Everyone. This presentation is made by me, Gauthier, and Ryan, and Frederic can come for personal reason. This presentation it's a technical report about our experience, and it's powered by Sense, a secure cloud provider, and at Sense we are all NixOS enthusiasts. So, in introduction, we will explain the both use case we face it, and why we decide to go on NixOS, and we will explain all the prerequisites needed to understand why we need, how we build our admin terminal, and we will talk about development process, and we will conclude. So, we have the first challenge is we are an organization that operates a critical IT infrastructures with some security requirements delivered by the French agency, and the regulation is named SecNumCloud, and imposed to have a secure administration terminal providing and complying with some hardware-rooted integrity guarantees and OS hardening. And we thought about simple workflow to onboard at the first boot our administrators. We decided to keep on NixOS because our development terminal are based on NixOS. The second challenge is it's for dual organization admin terminal. You have two organizations, A and B, and the first organization subcontracts to the second for helping to monitor a subset of operation of the critical infrastructures. But the both organizations are not trust between us, and they need to agree on the strict condition about building this OS image, which permit to build an administration terminal.
So I will talk more about why did we use NixOS. So, well, every year we have NixOS talks. We discuss this NixOS in this conference. So as said by Gauthier, NixOS was already the foundation of development terminals. There was already a lot of code, Nix code in the company. So it was a no-brainer to have an a production administration terminal that reuse these modules, these concepts. One thing that was particularly important to fulfill the requirements that Gauthier mentioned for SecNumCloud is everything that ParticleOS wants to bring to the desktop, to the servers, that is dm-verity, image-based updates, repartitioning, and so on and so forth. And this is, I would say, this is implemented via systemd-update, systemd-repart, systemd-storage TM, and so on and so forth. And NixOS is a systemd first distribution. So NixOS adopts a lot of systemd features, builds on the top of them, tests them, and exposes them for building as building blocks. And then, like, NixOS has a certain properties that makes it very, very easy to build compliance on the top of it, to assert that the system is in a certain condition, which was very appealing for, well, what we would making our result compliant for the auditors. And finally, we can also test the system automatically. And this was important to verify that we don't regress when we introduce complicated features, core features such as dm-verity, and so on and so forth. Okay. So I think most of you are familiar with this diagram, but very quickly to put you in the context of the boot sequence and boot measurement, so we rely on TPM2. And so TPM2 works in a way where everything gets measured as a chain, and the UEFI the UEFI BIOS code and the UEFI configuration gets measured. Then we boot the bootloader. Then the ESP partition information gets measured as well. The OS partition gets measured. And finally, we have in our partition layout in the system, in the administration terminal, we have only one partition that is not immutable. We will go more into details of what does it mean to be immutable. That is indeed mutable, but cannot contain any binary. All binary needs to live on immutable partitions. Immutable means dm-verity protected. And then you get the PCR's register as you're used to. So one problem that you have when you want to build such systems is that you need to predict what will be the PCR values after booting the system. So we built a tool for that called Augur, which we're looking to open source. And the idea of Augur is to take care of two types of measurements. The firmware, the hardware measurement that we don't control, the manufacturer does its own soup, and the software measurement that we do control. So for the firmware measurements, what we do is we take laptop in a lab, and we record, like a flight recorder process, we record what are the events that goes into the TPM via the TPM2 event log, and we create something called a baseline. And then we push this baseline in like some sort of storage, and we use it to predict any further measurements. And for the software, we can just take the build artifacts made by the CI and simulate measurement performed by the boot process, which are all kind of documented. Mixing the two of them gives us the full measurement of all PCRs, PCR 0, yes, to PCR 14, and we lock and guess all of PCRs. So we don't do secure boot, we do only measure boot. Many people have opinions on measure boot versus secure boot. In our case, we don't want to manage signing keys, we don't want to deal with all of that. We still need to sign some, of course, the updates, but that's a separate concern. We always want the device to be able to boot. We would rather be able to understand why a device doesn't pass a remote attestation rather than having it being locked. And we have dm-verity, which I think is one of the core features that secure our platform. And finally, those are laptops that SREs are using to admin the cloud. They need persistent personalization. This is something that we missed. We didn't let them configure Wi-Fi or record their Wi-Fi password and so on, or their bookmarks. And this proved to be a problem during operations. So we needed to invent a way to have safe persistent personalization. And this is an interesting topic. So Gauthier will go back for the end-to-end process.
Yes. How we decided to provide a hardware administration terminal. Like we already say, we need to have integrity guarantees, and for that we could achieve with hardware onboarding, immutable OS, measure boot, and doing remote attestation by the directly by the infrastructure. So first of all, we will have to do the hardware onboarding. We check the TPM manufacturer cert and the laptop manufacturer and generate endorsement key, attestation key, and store root keys and any certs in hardware inventory databases. And this is the same for all the firmware laptop onboarding. And then we have an OS source repo that contain all declaration for NixOS, and pipelines which will build predicted boot measure and the boot images. So now we need to deliver a ready-to-use laptop. We need to identify what the user need to do at the first boot, with some constraints which need strong security and privacy. For the first boot, we decide to allow user to define the username, the password, and the keyboard layout, and the rest of the system stay unchanged and immutable. And then for the disk security, we decide to realize all laptops must be encrypted with LUX and FIDO2, which is present in YubiKey. The benefits are strong authentication at boot. It permits to protect against disk theft and simplified the disk description phase. So the user have a laptop we shipped with an immutable NixOS image and hardware on board, set up with the wizards, and set its identity. And the setup apply a user account creation, system keyboard configuration, and LUX encryption. And then he reboots, and the laptop is ready, secured, and personalized. The critical infrastructure have some endpoints, one for updates, another for access endpoint, and one IDP endpoint. And the remote attestation happens when he wants to access to the critical infrastructure. And now we will talk about remote attestation procedures. This is defined by an RFC. The attester needs to provide an evidence to the verifier. The verifier contains endorsement, reference values, and some policy to attest with the relying party. When you do an update, you need to generate new PCR generation. So you have a PR, which will be reviewed by your peer, and then the CI/CD will generate prediction, and the terminal RATS verifier will sync with PCR prediction databases and hardware inventory databases. So at the end, you have an administration which will use a workstation with TPM. He unlocks the YubiKey. Then it will connect to the VPN, but he doesn't have access to the infrastructure directly. He needs to realize the remote attestation. If the laptop and all PCR are not conformed with data contained in the databases, he cannot access to the services contained in the infrastructure. And the remote attestation server will be issued trust token, and following the context which will be connected to the infrastructure, he could be accessed for some services or not. Now we will talk about how two organizations can work on one administration terminal. So the dual administration terminal, it's a fork of the secure admin terminal. And the org-B need to rebuild this image, have the capacity to rebuild the image, so we don't need to introduce non-reproducible packages. And if a package is not trusted by two organizations, they need a third party trusted by the both organization. This enables org A to manage that ecosystem, but also that the dual admin terminal OS image with org B, and org B may contribute features to the dual admin terminal and download OS update from their own servers. So in fact, we have this schema who you have the first organization which builds all the image, and the org-B can rebuild the image within its own build pipeline and normally have identical images between images generated by the first pipeline of org-A and org-B. And then the org-B need to realize also a remote attestation to access to the infrastructure of org-A, and need to have an IDP endpoint differently of the organization A and another update endpoint from the organization A.
So now I'll take over for development process and challenges. So developing this sort of laptop, so again contextualizing, we are developing a NixOS immutable workstation. Immutable means dm-verity. We want to develop and test all features in a pre-production environment. We don't want to take a real laptop, connect it to production, and flash and build on the top of that, because otherwise this introduces a lot of rebuild latency. Building an immutable system is slow, and we can't have a developer mode, or we can disable certain features, else we're not testing the real thing. And another challenge is we're not controlling the hardware. We are not the manufacturer, we don't control the BIOS, we just buy commodity hardware, and we have to make it work. We have some tools. We can have checkpoints, we can have a hardware onboarding phase that you saw, that help us to rectify some issue that we saw. So here it's a matter of developer experience. If you work on a hardened system, you don't have root, you can bring binaries out of nowhere. It can be a pain. So I think the first key is to have a virtual machine setup. Virtual machine setup cuts the latency to rebuild, because you just, using Virt.io and various things in the ecosystem, you can completely emulate an immutable block device at the virtual level, while on the host you can have something very mutable. So we inspired ourselves from someone who worked on the sys-update playground, which is just a repo trying to explain how to use systemd sysupdate in an image-based ecosystem with NixOS. And one thing that is really nice in this repo is a QEMU script to test everything. Based on this idea, you can expand it, and you can have a very nice test harness for this sort of laptop. And one thing that we added on the top of it is to add devices pass-through and network pass-through, so that we can connect a virtual machine virtualizing the hardware workstation to a pre-production environment and work on it directly. We didn't consider, for example, using emulated devices for security token, because, for example, if you take Kanoki QEMU, it's unmaintained, so it doesn't work very well. We were supposed to have Jules Lamour, who would have presented all these works, but he couldn't make for the conference, so credit where it's due. Another big problem is hardware PCR predictability. So we all want to use TPM2, remote attestation, encryption, locking against PCRs and stuff, but how much can you lock on actual hardware PCR today? The answer is we did the thing that we explained in the introduction, taking a baseline. We know these values. We want to verify they're stable across boots. But we are more interested if they're stable across consecutive serial numbers of the same family of laptop. So we buy two laptops. They have they're consecutive in the manufacturing process, and we look at their PCR lock dashboard, and we verify how they differ. And between two consecutive laptops, the usual divergences that we found are in the boot options, for example, because those laptops those days, they come up with default boot options using network boot. And the network boot doesn't do something like I will just connect to any network card I will find. I will use Wi-Fi, and I will encode in the UEFI path the MAC address of the Wi-Fi card. So this resulted in a change in PCR4. And every consecutive laptop that we found differed only by this value. So what do? There are two solutions. Either we record a baseline per serial number, so you have an immense repo of every laptop that you onboarded, and every of them has, a serial number and their hardware baseline. So you don't have to worry about is there stability of hardware PCR across a family of laptops, because you're recording the exact laptop baseline, or you can normalize UEFI variables at the onboarding phase and then eliminate any difference between those two laptops. We decided to do the first while we were working also on the second one to test how plausible it is to rely on this solution. But the conclusion is it's possible, it's very predictable, surprisingly, and the problems are simple to solve. Then we talked about a bit, and Gauthier touched on it, on the bit-to-bit reproducibility problem. So if you want to do the DIT idea, you need to have bit-to-bit reproducibility if you want to have the other organization not trust you. But actually, you also need to have the bit-to-bit reproducibility if you want to avoid having a golden image. That is an image somewhere that everyone pulls, that no one knows how to rebuild. If you rebuild it, then something breaks. And the problem we encountered is like, so this is in a hardware workstation, people are using it, people are working with it, and then someday some user comes and says, please can you just add this tool, I really need this tool to work on my workload and stuff, so they have vendor-specific binaries, debug tools, their new theme on new Vime, whatever. Cool. It's almost all in Nix packages, so it's like one line away in our code to just add the new thing. Sometimes they even send the PR themselves and they explain us how to add it, and it's like, yeah, okay, sure. Problem, it breaks the bit-to-bit reproducibility because Nix packages guarantee, or at least their story for bit-to-bit reproducibility, is guaranteed only in the scope of a core package set, like the default ISO installation and so on and so forth. It's not guaranteed for the whole package set, which is 100K of packages. And whereas like you may find maybe 800 packages in the default ISO install. So Gauthier touched on the idea. You can use a third party, a trusted third party, that has built a source of truth, a golden package version, and you can just pull from there. And you can both, as multiple organizations, pull from there. So for example, that trusted party can be cache.nixos.org. So that's one solution. Other solution is just don't include that tool. And why do we care about bit-to-bit reproducibility even inside of S3NS, even without the DAT use case? Well, if you have multiple regions, multiple availability zones that has a guarantee that they can operate independently, then your CI pipelines, the build pipelines that we showed earlier, they have to work independently. And independently means that you cannot use synchronization workflows to send like the source of truth of one CI to the source of truth to the other CI and so on. And so you need to have bit-to-bit reproducibility, otherwise it's impossible to produce the same predictions for the PCR. And the PCR drifts very quickly because the output of the CI factories are different, so it causes different output path in the Nix store. Output path in the Nix store being different means runtime variation in dm-verity hash, and runtime variation in dm-verity hash means runtime variation in the kernel command line. And the kernel command line gets measured by the TPM. So you have PCR drift. So one other solution, which is a bit sad, but can be used temporarily, is to reintroduce golden image. That is to do the synchronization, the replication from one CI factory to another, or that you coordinate the build on one availability zone. But this is like an interesting situation where bit-to-bit reproducibility is critical. And then there is like this thing. So we wanted to lock on all PCRs. And I said we lock on all PCRs, but I lied a bit. We don't lock on PCR5 because PCR5 is a bit weird. So what does PCR5 does? It does a bunch of things, but one thing it does, it's measure the GPT partition table header. And the GPT partition table header, what does it contain? Okay, it contains partition types, whether it's a Linux root file system, a swap, or anything. Those are fixed. They're predictable, okay. It contains disk UIDs. So you would expect that disk UIDs would be random, but you could fix one. But you can't. If you're using systemd-repart setup generator, for example, it relies on the UID, extract a part of it, and use this to learn the dm-verity hash. So disk UIDs varies as the dm-verity hash varies. Okay. And then partition labels. So systemd-update, for example, uses _empty to discover an empty partition where to install the new update. And then renames the label. Okay. So this is not fixed as well. And then disk sizes. So this one is a more, I would say, questionable one. But these sizes can change if you service a laptop and you upgrade a 512 gigabyte SSD to 1 terabyte SSD. And so sizes and offsets will change as a result if you grow the partitions. And everything of that gets measured in PCR5. So if you do an update or anything, your PCR5 changes completely and in a way that can be very difficult to predict. So how to put PCR5 under control in presence of a ParticleOS? This is an open question to the audience. And it's a bit like, what is the threat model of PCR5? Why are we measuring these values? What are we trying to defend ourselves against? And should we make changes to how we are seeding those values to support PCR5 if we believe there is a problem? So we're coming to the conclusion. So I'm not sure the introduction makes it clear, but S3NS is operating a SecNumCloud Google Cloud region. So we run a GCP region, and the SAT is a tool to admin this GCP region, notably. And my takeaway, or the takeaway I would like to give, is that NixOS might not be a 100% ParticleOS, pure ParticleOS, the way the ParticleOS developers meant it. But I think in the past years we pursued that ParticleOS philosophy, and we can see here that we applied everything together and we made a concrete tool that people are using on the top of it, which ticks a lot of compliance cases and is very interesting to work with. dm-verity, systemd-repart, TPM2, sysupdate. Hardware PCR are surprisingly well behaved, at least in the same SKU. We didn't try with new SKUs. Reproducibility is not free, it's a business cost. Like we have users coming and asking new packages. This makes our reproducibility weaker. How do we control that? What are good ways, guidelines to handle this problem? PCR5 is weird, as you heard. And then I think one key takeaway we learned, but we don't talk too much about it, is persistent personalization. Like it's often forgotten in such laptops where people would just give them like some dry workstation and they can't do anything in there. I think it's very important to actually inverse the relationship, not give them a dry workstation, but work from the start with them, and perhaps having like a non-secured workstation first, and then collect the requirements and put them inside the hardened workstation. Because sometimes even the users themselves, they don't know what they want. They take it for granted, and it's very hard to actually say it. So it's better to learn it than to collect it via, I don't know, design thinking or anything. And yeah, building on the top of the SAT and Nix semantics, we created new use cases. So the development use case, the dual organization use case, which came up as we had needs, which is very interesting. And then we have some wish list. Of course, we need to work on it as well. But interestingly, so one problem that came up very early is that systemd update doesn't do delta or incremental updates. At some point, when your images are big enough to be gigabytes range, and that you have a shitty Wi-Fi corporate thingy, it becomes a major user pain point. But more than that, actually, long-term storage of full images is very expensive, so you could rotate them and so on, but also, if we could make them cheap to store, this wouldn't be a problem. And then, fragile HTTP connections happens all the time. So I feel like systemd update is not super reliable in this context. So we would be interested to like work on having something like the Twig store, which was presented in 2023, to have like content addressable blocks of updates and downloading only the delta, what changed, and so on. A big wish list of mine is like having an open source and collaborative crowdsourced database of known information on hardware PCR behaviors of laptops and hardware and whatever. And could be like a UAPI group project, if this even makes sense. Like could be a big spreadsheet. Doesn't have to be complicated. Building reference remote attestation values is like we had to come up with our own tool, Augur. I know some other people also came up with their own tools. Can we converge on this, standardize some things, and make remote attestation even easier to use for everyone? And maybe connect it to something like Spire policies for machine identities that were presented yesterday. And then another topic is telemetry and diagnosis. So someone has remote attestation failing. How do we understand what is going on? What value change? What is the problem? So right now what we do is we send an engineer, and the engineer pulls PCR log, compares, and says, oh yes, here, you plug the USB stick, so you can't access the production now. And can you remove the USB stick at the boot so that you can access the production? So can we go further on this and makes it easier, self-service, like nicer? And I think that's pretty much it. I don't know how much time we have for questions, but yeah.
You have about 8 minutes.
8 minutes, okay.
So actually a fair bit of time. Does anyone have any questions?
There's like a question at the back and a question here.
So you mentioned a problem being the reproducibility of the packages in Nix package, where you said it's only a core set that's more or less guaranteed to be reproducible. Looking at other distributions, I think Debian is now at 93% or so of reproducibility. Did you look into tackling the reproducibility issues of the packages that you rely on? So instead of working around with your global golden image, instead extending the set, and what kind of challenges you faced there that could potentially not be drawn from the experiences of other distributions?
So I think the Debian reproducibility, the Arch Linux reproducibility, many distribution reproducibility also applies to what they consider a core package set. And I think we share a lot of these packages that are both reproducible on their side and our side. The problem stems from the fact that so sometimes the software such as Python will regress on bit-to-bit reproducibility, and it takes like serious expertise to fix this sort of problem. But well, if it applies to Python, then it will be very hard to get rid of Python in general. But some people succeed to get rid of many interpreters, so who knows? The other type of problem we encounter is that user adds their own package with their own packaging, and telling them or explaining them how to do bit-to-bit reproducible packaging is also a cost. So we are not looking into doing this sort of teaching right now. It is not a problem because we don't want to have that many software on the hardware workstation. One solution would be to move all this software behind the critical infrastructure and have like some sort of virtual machine that contains all these software considered as a black box. And this would enable also more interesting things where we don't have to force people to package things for NixOS. They could have their own VM on Debian, on Red Hat, on Windows, on whatever, and they can do their work, which is workload specific. And then not everyone has to share the same set of tools. They could be VMs for networking work, VMs for higher level components work. So that's why we're going more into that direction than tackling the bit-to-bit reproducibility problem. I hope this is a clear answer. Or, okay.
Any further questions? Oh, there you go. Sorry.
Didn't they make a version 2 of the event of the GPT partition table? And does that one solve the issues? I haven't seen anybody use that event ever, but there is a same name of the event 2 version that I think at least singles out the UUIDs and stuff.
So I didn't notice it, even though I read, as you know, I read the source code of Tiano Core EDK2 for a long time. But what I wonder is, even if there is the version 2 of the event, how do you tell the BIOS to use the version 2 of the event while measuring? I don't think this option seems obvious or clear somewhere. So I feel like the solution is probably to go see manufacturers and say, what gives? What do we do?
Okay. Well, let's thank Ryan and Gaultier for their presentation.